Strengths of acids and bases. We'll first look at acids. Strong acids ionize completely in water. There are 6 strong acids. You just have to know these 6 strong acids. If it's a strong acid and I put it in water, it completely ionizes, which means this. If I put HCl in water, it will completely break apart into H plus and Cl minus. So that's what completely ionizes means. It breaks apart completely, 100%. Look at the example. Calculate the pH of a 0.002 molar solution of HBr. So HBr is a strong acid. When I put it in water, it completely ionizes into H plus, Br minus. Concentration of HBr is 0.002. Since it is a strong acid, the concentration of H plus will also be 0.002 because it's a strong acid. Completely ionizes. So to get the pH, I'm going to take the negative log of H plus, so negative log of 0.002, and that will give me the pH of this strong acid solution. pH comes out to 2.7. Weak acids, in contrast, ionize only slightly in water. Weak acids include any acid that is not a strong acid. So you know the 6 strong acids. If it's not one of the 6 strong acids, it's a weak acid. Weak acids follow the Bronsted-Lowry definition. So for example, HClO is a weak acid. When you put it in water, it produces ClO minus because acids lose a hydrogen and hydronium. We're going to use an acid dissociation constant, Ka, for weak acids, and it's a ratio of the ionized form to the non-ionized form. So Ka for this example up here would be equal to H3O plus times ClO minus divided by concentration of HClO. We leave out water because water is a liquid and the concentrations of liquids do not change. Let's look at this example right here. We have acetic acid. We're given the Ka value. So I know it's a weak acid. We're going to write the equation. Acetic acid plus water forms H3O, hydronium, plus acetate. The concentration of acetic acid is 0.2 molar. We don't worry about the concentration of water because it's a liquid. Since the coefficients in front of H3O and acetate are both 1, I will use X's for those. Ka expression looks like this for the weak acid. Products divided by reactants. So H3O times acetate over acetic acid. Plug in our numbers. Ka is 1.8, 10 to the negative 5. Set that equal to H3O is X, acetate is X, divided by acetic acid, which is 0.2 molar. When we solve for X, that will tell us the hydronium, H3O, which comes out to 0.0019 molar. So there's hydronium. If I want hydroxide, which is OH, I know that H3O times OH equals 10 to the negative 14th. So I would take 10 to the negative 14th and divide by 0.0019. OH comes out to 5.3, 10 to the negative 12th molar. So that's how we would do a weak acid problem. Now let's look at bases. Strong bases, just like acids, ionize completely in water. So when I put a strong base in water like KOH, it's going to completely break apart into ions, K plus and OH minus. Notice all the strong bases, they contain hydroxide. So if it contains hydroxide, it is a strong base. Let's look at an example. Calculate the pH of a 0.0034 molar solution of NaOH. Well, NaOH is a strong base. So when I put it in water, completely ionizes Na plus and OH minus. Concentration of NaOH, 0.0034. Since it's a strong base, the concentration of OH is also 0.0034. In order to calculate the OH, I can find the pOH by taking the negative log of 0.0034. The pOH comes out to 2.47. Now I want the pH, and I know the pH plus 2.47 equals 14. So the pH, I would expect it to be basic, comes out to 11.53. And it is basic, 11.53. Weak bases, just like weak acids, ionize only slightly in water to form hydroxide ions. A couple examples, NH3 and Na2SiO3. So again, we're following the Bronsted-Lowry. When you put a weak base in water, bases pick up a hydrogen, so NH3 becomes NH4, but you also produce hydroxide. Just like we had an acid dissociation constant, we have a base dissociation constant, Kb. For the example up here, Kb would be equal to NH4 times OH divided by NH3. And again, we leave out water because the concentration of liquids do not change. Let's look at a weak base problem. NH3 is my solution, so we have NH3 plus water. NH3 is going to pick up a hydrogen to form NH4, and then you're going to get hydroxide because it's a base. My concentration of NH3 is 0.3 molar. We're going to forget water because it's a liquid. On the product side, NH4, we're going to use X, and OH, we're going to use X because the coefficients in front of those are 1 to 1. So we have Kb, which is 1.8 times 10 to the negative 5 is equal to X times X divided by 0.3. We're going to solve for X, which is going to be hydroxide. So hydroxide ion comes out to be 0.0023 molar. And then to get hydronium, we know OH times H3O plus equals 1 times 10 to the negative 14th. We'll use that equation again. So hydronium comes out to 4.3, 10 to the negative 12th molar.